Hello everybody, good morning. Myself Dr. Shubhankar Sen, an Associate Professor from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the second lecture of the fifth module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the implementation of the convective as well as radiative boundary conditions in one dimension as well as in two dimensions. Both of these boundary conditions, they augment the coefficient matrix besides updating the element level load vector. The radiative boundary condition, as we have already shown in the previous weeks, it introduces nonlinearity into the element level and finally the global matrix equation system. Now we shall illustrate the implementation of the convective boundary condition. Implementation of the convective boundary condition in two dimensions. So let us consider the square domain again. So this is omega, this is x-axis, this is y-axis. At the right side boundary, we have the convective condition. So we consider a bilinear quadrilateral element at the right boundary. So this is the bilinear quadrilateral element at the right boundary with local nodes 1, 2, 3 and 4. So dimension of the element, this is given as, this is delta x, this is delta y, this is the x-axis and this is the y-axis. So now we are showing it in close-up. So we have the element E, local nodes 1, 2, 3 and 4, and this is H T infinity. So the boundary, this is denoted by the symbol gamma C for the convective boundary. From the weak form of Poisson equation, of heat conduction, we know that the convective boundary condition contribution comes from the integration over gamma E psi I H into T infinity minus T d gamma E term. Now integration along gamma E, we take H as constant, psi I E T infinity minus summation of T j E psi j E, j equals to 1 to n, thus belongs to gamma C d gamma E. Now T2E and T3E are unknown temperatures. So we have T1E, we have T2E, we have T3E, and here we have T4E. So all four temperatures, including at the boundary, T1E, T2E, T3e and T4e, all four temperatures are unknowns. So this expression we can simplify as H into boundary integral over gamma e psi ie T infinity d gamma e minus, this is represented as H into summation over j belongs to eta c, integration over gamma e psi ie psi je d gamma e d gamma ce, we can write it as into tje. Now the effect of CBC or convective boundary condition is limited only to the boundary nodes. Therefore, similar to NBC, a four-noded bilinear quadrilateral reduces to a two-noded bar element while implementing the convective boundary condition. So, our four-noded quadrilateral it reduces to a two-noded bar element. So this is the original element. This is of size delta y. This reduces to a two-noded bar element, local nodes 2, 3, h, t infinity. This dimension is delta y. This is gamma c. This is T2e. This is T3e. This is element E. So T2e and T3e, they are the unknown temperatures. Now we go back to the integrand expression. So the CBC expression simplifies to h t infinity integration along gamma ce psi ie d gamma ce, since the effect of the convection it does not reach the interior edges, so we are dealing only with the boundary edge, minus summation h integration along gamma ce psi ie psi je d gamma ce into tje. Therefore, from the convection boundary condition, the contribution to the element level stiffness matrix comes from H summation over J belongs to gamma CE integration along gamma CE psi IE psi JE d omega E TJE term and the load vector contribution is H T infinity integration over gamma CE psi IE d gamma CE. So this should be d gamma CE. Let us first consider the augmentation of the element level stiffness matrix by H summation j belongs to gamma CE integration along gamma CE of psi IE psi JE d gamma CE into TJE. So this is the boundary. We have the element E with local nodes 2 and 3. This is delta Y. So temperatures at these two nodes are T2E and T3E. For convective boundary condition, we have H and T infinity, and this is our gamma C. So for this case, I is varying from 2 to 3 and J is also varying from 2 to 3. So we have Kije convection equals to H into integration over gamma CE psi IE psi JE d gamma CE. For I equals to 2 and J equals to 2, we have K22E convection equals to H integration along gamma CE psi 2E d gamma CE equals to H integration along gamma CE psi 2E whole square d gamma CE equals to H into integration minus 1 to 1 psi 2E is half into 1 minus eta whole square d gamma CE. This is delta Y. So dy will be Jacobian determinant into d eta. So this is delta Y by 2 into d eta. So this gives us H delta Y by 2 into 1/4 into integration minus 1 to 1 1 minus eta whole square d eta equals to H delta Y by 8 integration minus 1 to 1 1 minus 2 eta plus eta square d eta. This gives us, from here we get K22E convection equals to H delta Y by 8 into eta minus eta square plus eta cube by 3 varying from -1 to 1. This gives us h delta y by 8 1 minus 1 plus 1/3 minus -1 minus 1 minus 1/3. This comes as h delta y by 8 into 1/3 plus 2 plus 1/3 equals to h delta y by 8 into 2 plus 2/3 equals to h delta y by 8 into 8 by 3. This is h delta y by 3. Similarly, for I equals to 1, j equals to 2, for I equals to 2, j equals to 3, k 2 3 conv E equals to h integration along gamma ce psi 2e psi 3e d gamma ce equals to h integration -1 to 1. Psi 2e is half into 1 minus eta. Psi 3e is half into 1 plus eta. By taking their product, we get 1/4 into 1 minus eta square. So it comes half of 1 minus eta into half of 1 plus eta into determinant of je into d eta. So this gives us k 2 3e convection equals to h by 4 integration -1 to 1 1 minus eta square. Determinant of Jacobian is delta y by 2 into d eta equals to h delta y by 8. Then we have eta minus eta cube by 3. This gives us h delta y by 8 from -1 to 1. We have 1 minus 1/3 minus -1 plus 1/3. This is equals to h delta y by 8 into 1 minus 1/3 plus 1 minus 1/3. This is h delta y by 8 into 2 minus 2/3 equals to h delta y by 8 into 4 by 3 equals to h delta y by 6. Now this gamma ce psi ie psi je d gamma ce gives symmetry if we interchange I and j. Therefore k 32e equals to k 23e equals to h delta y by 6. It can be shown that k 33e convection equals to K22E convection equals to H delta Y by 3. Therefore, the convection matrix augmentation may be cast as H delta Y by 3, H delta Y by 6, H delta Y by 6, H delta Y by 3. With it, we had the temperatures. So this will be T2E and T3. Since the element level stiffness matrix Kije conduction is of 4 by 4 size, the augmentation by convection is also presented as a 4 by 4 matrix. So here it is 2 by 2, 2 by 1. Ke conduction equals to K11E, K12E, K13E, K14E, K21E, K22E, K23E, K24E, K31E, K32E, K33E, K34E, K41E, K42E, K43E, K44E. So, Ke conduction into Te, it can be written as T1E, T2E, T3E, T4E. Similarly, we can represent Ke convection into Te equals to T1E, T2E, T3E and T4E. So this T1E and T4E, they do not have any contribution in this convection matrix. So all the terms in the first and fourth row, they will be 0. So this 4 by 4 matrix will have a 0th row for the first and fourth row. So we have similarly the first column and the fourth column, we have the 0 terms as the entry. So this K22 term which we have calculated, this came as H delta Y by 3, K23 was H delta Y by 6, K32 was H delta Y by 6 and similarly K33 was H delta Y by 3. So this is the augmentation matrix. Augmentation matrix due to CBC. This K convective, it is a symmetric matrix. Now we can combine these two equations because both are linear in nature. So the augmented stiffness matrix due to CBC may be presented as Ke conduction plus Ke convection into Te equals to K11E, K12E, K13E, K14E, K21E, K22E plus H delta Y by 3, K23E plus H delta Y by 6, K24E, K31E, K32E plus H delta Y by 6, K33E plus H delta Y by 3, K34E, K41E, K42E, K43E, K44E. So this is the augmented matrix of 4 by 4 size, and the unknown vector is T1E, T2E, T3E and T4E. For the convective boundary condition does not hamper the symmetry of the matrix due to the conduction term. So augmentation due to CBC preserves symmetry of the stiffness matrix due to conduction or diffusion. Now we have the remaining load vector term. Let us now consider the load vector contribution FIE convection equals to HT infinity integration over gamma CE psi IE d gamma CE for I equals to 2 and 3. For I equals to 2, F2E convection equals to HT infinity integration from -1 to 1 psi 1E eta d gamma CE is dy d gamma CE equals to dy equals to determinant of the Jacobian matrix into d eta equals to delta y by 2 into d eta. This we have already discussed multiple times in the chapter of isoparametric formulation. So this is determinant of y by 2 into d eta. This is equals to h t infinity delta y by 2 integration from -1 to 1 half of 1 minus eta d eta equals to h t infinity delta y by 4 into eta minus eta square by 2 from -1 to 1 equals to h t infinity delta y by 4 into 1 minus half minus -1 minus half equals to h t infinity delta y by 4 into 1 minus half plus 1 plus half equals to h t infinity delta y by 4 into 2 equals to h t infinity delta y by 2. For I equals to 3, similarly we can find F3E due to convection equals to h t infinity delta y by 4 into integration -1 to 1 1 plus eta d eta equals to h t infinity delta y by 4 into eta plus eta square by 2 from minus 1 to 1 equals to h t infinity delta y by 4 to 1 plus half minus 1 minus half plus half equals to h t infinity delta y by 4 into 2 equals to h t infinity delta y by 4. So the load vector is modified as F2e convection equals to h t infinity delta y by 2 plus q into integration over omega e psi I e d omega e. This is the source term, and F3e equals to h t infinity delta y by 2 plus q into integration over omega e psi 3e d omega e. This is psi 2e. Therefore, Fe convection equals to F2e F3e due to convection equals to h t infinity delta y by 2 1 1. Therefore, for the 4-noded bilinear quadrilateral element, the convective load vector may be presented as Fe 4 by 1 due to convection equals to h t infinity delta y by 2 0 1 1 0 4 by 1. So this is for local node 1, this is for local node 4, and remaining 2 are for local nodes 2 and 3. Now we shall illustrate the implementation of the convective boundary condition in one dimension. So let us consider an one-dimensional problem. At the right end of the bar we have h and t infinity specified. Now we know that the weak form provides the CBC contribution in the RHS as boundary integral along gamma CE psi IE t infinity minus t d gamma CE. We have already shown the simplification of this integrand in terms of two-dimensional quadrilateral bar elements. Now, in one dimension, let us consider a two-noded bar element E with local nodes 1 and 2 such that the local node 2 is exposed to the convective boundary. So here we have H and T infinity as CBC. Our temperatures T1E and T2E both are unknown quantities. So for this case, the element level matrix equation will look like the element level matrix equation system is KET equals to FE or KE. This is a 2 by 2 matrix. T1E, T2E equals to F1E, F2E due to source plus F1E, F2E due to CBC. Now, this is the conduction or diffusion matrix. The element, this is a boundary element. So, this element we have taken at the rightmost extremity of the domain shown. So, this is x equals to 1, for example. This is x equals to 0, and this is the mesh size delta x. Now, the integrand we can simplify here. The integrand, the CBC integrand is simplified as boundary integral along gamma CE psi IE. Here one H is there, the convective heat transfer coefficient, H T infinity d gamma CE minus boundary integral along gamma CE H into psi IE T d gamma CE equals to H T infinity integration along the boundary integral gamma CE psi IE d gamma CE minus H into boundary integral along gamma CE psi IE summation TJE psi JE d gamma CE. This gives us H T infinity boundary integral of psi IE d gamma CE along gamma CE minus H into summation over J. J belongs to gamma CE psi IE psi JE d gamma CE into TJE. Now, the augmentation matrix due to convection BC is computed as, this comes to the left hand side of the matrix equation system. So this term is now becomes positive. So this is H into summation over J belongs to gamma CE psi IE psi JE d gamma CE multiplied with TJE. Now, the two-noded bar element reduces to an one-noded point element in relation to implementation of CBC. So, this two-noded bar element 1, 2 with H T infinity element E, this is delta x. So, This reduces to a single noded point element with h and t infinity as the boundary conditions. So for this point element we have psi 1 e equals to 1. So this is single noded point element at the boundary. So this expression for augmented matrix, so here the integration symbol was missing. Here the boundary integral is missing. It looks like the convection matrix contribution looks like k ije convection equals to h summation over j belongs to gamma ce integration over gamma ce. This is the boundary integral. This was psi ie psi je d gamma ce psi ie psi je d gamma ce. Now for this case, this rightmost boundary node I equals to j equals to 2 and psi 2e equals to 1 for single noded point element. This gives us k 2e convection equals to h into boundary integral over gamma ce psi 2e whole square d gamma ce equals to h into integration along gamma ce 1 square is 1 d gamma ce equals to h into cyclic integral of d gamma ce along gamma ce. This integrand must be equals to 1 so that the entire convective heat flux it goes to the boundary node only. So this is becoming equals to h and there is no contribution to the local node 1. So this CBC does not influence the internal node 1 and hence K11, K12 and K13 E terms are not augmented due to CBC. So it means that K11E convect equals to 0, K12E conv equals to 0 and K13E conv equals to 0. Therefore, the convection matrix due to CBC is presented as KE conv equals to 0, 0, 0, H and the stiffness matrix after augmentation looks like K conduction T plus K convection TE. This becomes equals to K11E, K12E, K21E, K22E. This is due to conduction. The unknown temperatures are T1E and T2E. Due to convection, the augmentation is only for the K22E term. So we have the convection matrix with T1E and T2E. So this is K due to convection and this is stiffness matrix due to conduction. So we can combine both of them and this gives us K11E, K12E, K21E, K22E plus H, T1E, T2E. This will be K21E and this will also be K21E. This is K conductive, this is K convective E and E. For the load vector, FIE due to convection equals to H T infinity into integration along gamma CE psi IE d gamma CE. This is H T infinity into gamma CE d gamma CE, since psi 2E equals to 1 at I equals to 2, because I equals to 2 represents a single noded point element. This gives us H T infinity. Therefore, the final element level matrix equation system for the CBC problem in one dimension leads to KE conduction into TE plus KE convection into TE equals to FE source plus FE due to CBC. This gives us K11E, K12E, K21E, K22E, T1E, T2E plus 0, 0, 0, H, T1E, T2E equals to FE due to source plus 0, H, T infinity. So we can combine the left hand side as K11E, K12E, K21E, K22E plus H, T1E, T2E equals to F1E due to source. Here we have F2E due to source plus H T infinity. Now, in the previous weeks, we have shown that if our governing equation is K del square T plus Q equals to 0 gives Ke equals to K by delta x minus K by delta x minus K by delta x, K by delta x and Fe source equals to Q into delta x by 2 delta x by 2. Putting these expressions for Ke and Fe, we can further simplify this matrix equation system. So we can further simplify as K by delta x minus K by delta x minus K by delta x, K by delta x plus H is a 2 by 2 matrix, T1e, T2e equals to Q delta x by 2, this is Q delta x by 2 plus H. So this is the element level matrix equation system in 1D for a two-noded bar element subject to CBC. So this is the augmented matrix due to CBC. So the augmentation of the stiffness matrix due to convective boundary condition does not include any modification of the symmetry of the matrix. So the matrix remains symmetric after addition of this convective heat transfer coefficient. Here the T infinity is missing. This should be H T infinity. Now we illustrate the implementation of the radiative boundary condition in 2 dimensions first. So here we go with implementation of radiative boundary condition in 2 dimensions. So let us first consider one slab. This is omega. We have the governing equation K del square plus T, K del square T plus Q equals to 0. And then at the right boundary, we have the radiative boundary condition. We denote this as gamma R. So at the right boundary, we are provided with absorptivity alpha, emissivity epsilon, and the heat received as QR double dot. So we consider a 4-noded bilinear quadrilateral element at the right boundary and illustrate the boundary condition implementation. So we consider one element E with local nodes 1, 2, 3 and 4. So the dimension of this element is delta x in the x direction and delta y in the y direction. So this is x axis, this is y axis, this is y, and this is x. So our given boundary condition data are for alpha, epsilon and QR double dot. So unknown temperatures for this element are T1e, T2e, T3e and T4e. The temperatures T1e, T2e, T3e and T4e are all unknowns. The RBC influences only the boundary edge and hence the element reduces effectively to a two-noded bar element. So here we show the bar element with local nodes 2 and 3. These remaining edges we show as dotted, node 1, node 4. This is delta y. Here we have QR double dot, we have alpha and we have epsilon. So this is gamma RE. So the temperatures at the boundary are T2E and T3E. From the weak form, the RBC contribution is given by boundary integral over gamma RE psi IE into alpha QR double dot minus epsilon sigma into T to the power 4 d gamma RE, where sigma equals to a constant 5.6697 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Now this temperature T is in Kelvin. This we have highlighted in the previous lectures also. Now this integral term we can split into two parts. One part contributes to the element level stiffness matrix and the other part contributes to the element level load vector. So let us split these components first. So this gives us boundary integral along gamma RE psi IE alpha QR double dot minus boundary integral along gamma RE psi IE epsilon sigma T to the power 4 d gamma RE. So d gamma RE. So this gives us alpha QR double dot boundary integral along gamma RE psi IE d gamma RE minus epsilon sigma boundary integral along gamma RE psi IE into summation of TJE psi JE to the power 4 d gamma RE, where J belongs to gamma RE. This can be further simplified as alpha QR double dot minus boundary integral of gamma psi IE d gamma RE along gamma RE minus epsilon sigma summation over J belongs to gamma RE psi IE psi JE to the power 4 d gamma RE TJE to the power 4. Now the first part, it contributes to the element level load vector, and the second part, it contributes to the element level stiffness matrix. Evidently the element level stiffness matrix gives rise to non-linearity, so its sign changes when it goes to the left hand side. Let us first deal with this augmenting matrix. Here this is not a minus sign, this is a product, and here the integration symbol is missing. So the radiation matrix is first computed from Kij E K IJE radiation equals to epsilon sigma into summation over j belongs to gamma RE psi IE psi JE to the power 4 d gamma RE. Here I is varying from 2 to 3 and j is also varying from 2 to 3 because the local nodes 2 and 3, they are exposed to the radiative boundary condition. So this is the mesh size delta y, and here we have alpha, epsilon and QR double dot. So here we shall get a 2 by 2 matrix equation system for the radiation contribution. We consider the matrix first. So consider I equals to 2, j equals to 2. This gives us the individual term here. The individual term is, so here we can skip the summation symbol. So this is with TJE, with TJE. Now by removing this temperature, we can remove the summation symbol and simply we write the stiffness matrix for augmentation. So this is K22E equals to epsilon sigma integration along gamma RE psi 2E to the power 4 d gamma RE equals to epsilon sigma integration along gamma RE psi 2E to the power 5 d gamma RE. Now this gamma RE, this represents the edge 2, 3. So this is along a path or a line. So we can simplify it as epsilon sigma integral along path 2, 3 psi 2E to the power 5 into dy. So dy is the height of the element. Now we perform this integration in the natural coordinate system. So we can write it as epsilon sigma integral minus 1 to 1. Now this psi 2E is half of 1 minus eta to the power 5 dy equals to determinant of the Jacobian into d eta. So this is delta y by 2 into d eta. So this is delta y by 2 into d eta. We get here epsilon sigma delta y by 2 integration from minus 1 to 1 by 2 to the power 5 into 1 minus eta whole to the power 5 d eta equals to epsilon sigma delta y divided by 2 to the power 6 integration minus 1 to 1 minus eta to the power 5 d eta. Let us consider 1 minus eta equals to p. This gives us when eta equals to minus 1, p equals to 1 minus 1 equals to 2, and when eta equals to 1, p equals to 0. So d eta equals to minus dp. These we substitute here to perform the integration. This is epsilon sigma delta y by 64, 2 to the power 6 is 64. Now the limit of the integration, it is from 2 to 0. 2 to 0, 1 minus eta is p, so it is p to the power 5 and d eta is minus dp. So minus dp, this is equals to minus epsilon sigma delta y by 64 into p to the power 6 by 6. It is varying from 2 to 0. So here we can write it as minus epsilon sigma delta y by 64 into 1 by 6 into 0 minus 2 to the power 6. This gives us, this minus and minus will be plus. So we are left with epsilon sigma delta y by 64 into 1 by 6 into 2 to the power 6 means again 64. So we are left with epsilon sigma delta y divided by 6. So this is the contribution from the radiative boundary condition to the K22E term. Now this we can try to evaluate by using Gauss quadrature. Okay, so evaluate K22E by Gauss quadrature. So if we look into the integrand, our integrand was a fifth order polynomial. We have 1 minus eta to the power 5, or we have p to the power 5 into dp. So our integrand is epsilon sigma delta y by 2 to the power 6 into integration from minus 1 to 1 minus eta to the power 5 into d eta. So in this case our number of Gauss point will be the power of the polynomial plus 1 divided by 2. So power of the polynomial is 5. This is a fifth degree polynomial. The integrand 1 minus eta to the power 5, it has the coefficient term as 1 into eta to the power 5 at the last. So we can consider the polynomial as fifth degree. So this is 5 plus 1 by 2. So this is 3. It means that we have to perform a 3-point quadrature. Therefore, we have to perform a 3-point quadrature. Okay, so the integrand I equals to epsilon sigma delta y by 64 integrand minus 1 to 1 minus eta to the power 5 d eta equals to epsilon sigma delta y by 64 into summation of I equals to 1 to 3, ngp is 3, f of eta I wi, where f of eta equals to 1 minus eta to the power 5. So we rewrite this integrand as I equals to epsilon sigma delta y by 64 into summation from I equals to 1 to ngp is 3, f of eta I wi, where f of eta, it was 1 minus eta to the power 5. So this was our element. This is the eta direction. So this is local node 3, this is local node 2, this is our gamma r e. So this transform to the element -1 to 1 in the eta direction. So local node is 2, local node is 3. So our integration points, they are minus square root of 3 by 5. This is 0. This is square root of 3 by 5. It is 0.7746. This is minus 0.7746. So this is the quadrature point 1. This is quadrature point 2 with eta equals to 0. And for quadrature point 3, we have eta equals to 0.7746. Now, the Gauss weights are here. This is 5 by 9. This is 8 by 9. And this is 5 by 9. So this is W3. This is W2. And this is W1. So this is quadrature point eta 1, this is quadrature point eta 2, and this is quadrature point eta 3. So this can be written as epsilon sigma delta y by 64 into the integrand is epsilon sigma delta y by 64 into f of eta 1 w1 plus f of eta 2 w2 plus f of eta 3 w3. This we can simplify as epsilon sigma delta y divided by 64. F of eta 1, f of eta was 1 minus eta to the power 5 at eta equals to minus square root of 3 by 5 into w1 into 5 by 9. F of eta 2, this is 1 minus eta to the power 5 at eta equals to 0 into 8 by 9. The last contribution is 1 minus eta to the power 5 at eta equals to square root of 3 by 5 into 5 by 9. So we can simplify this expression epsilon sigma delta y by 64. So the first term comes as 1 plus 0.7746 to the power 5 into 5 plus 1 minus 0 to the power 5 into 8 plus 1 minus 0.7746 to the power 5 into 5, the entire quantity divided by 9. So this simplifies to epsilon sigma delta y by 64 into 9. Here we have 5 into 1.7746 to the power 5 plus 8. So 1 to the power 5 is 1 plus 5 into 1 minus 0.7746. So 46 will give us 54. So it will be 0.2254 to the power 5. We can simplify this expression, and then from there we can cross check whether this expression is leading to the value which we got through the exact integration. Our exact integration yielded K22E equals to epsilon sigma delta y by 6. So this I is actually K22E. Now we calculate the off diagonal term K23E. Now calculate the off diagonal term K23E. So I equals to 2, J equals to 3. This gives K23E equals to epsilon sigma. Here we look into the generic expression. Our expression was epsilon sigma into integration over psi ie into psi je to the power 4 d gamma e. So this expression was epsilon sigma integration along the path 2, 3 psi ie psi je to the power 4 d gamma re for I equals to 2 and j equals to 3. So this gives us K23E equals to epsilon sigma into integration along the path 2, 3. So we have psi 2e into psi 3e to the power 4 into dy. So this gives us epsilon sigma integration from -1 to 1 psi 2e eta into psi 3e eta to the power 4 into delta y by 2 into d eta equals to epsilon sigma delta y by 2 integration -1 to 1 psi 2e into psi 3e to the power 4 d eta. This gives us K23E equals to epsilon sigma delta y by 2 integration from -1 to 1 psi 2e psi 3e to the power 4 d eta equals to epsilon sigma delta y by 2 integration from -1 to 1 half of 1 minus eta into half of 1 plus eta to the power 4 d eta. This gives us epsilon sigma delta y divided by 2 to the power 6 integration from -1 to 1 1 minus eta into 1 plus eta to the power 4 d eta. Let 1 plus eta equals to p. When eta equals to -1, p equals to 0, and eta equals to 1, p equals to 2, and d eta equals to dp. So this gives us epsilon sigma delta y by 2 to the power 6. The limit of integration, this is from 0 to 2. The first term is 1 minus eta. Now 1 plus eta equals to p. This gives us eta equals to p minus 1, or minus eta equals to 1 minus p. This gives us 1 minus eta equals to 2 minus p. So here we can put in place of 1 minus eta the expression of 2 minus p, and 1 plus eta is itself p. So this is p to the power 4, and d eta equals to dp. So this we can write as epsilon sigma delta y by 2 to the power 6 into integration from 0 to 2. It is 2 p to the power 4 minus p to the power 5 dp equals to epsilon sigma delta y by 2 to the power 6, 2 into p to the power 5 by 5 minus p to the power 6 by 6. So this gives us epsilon sigma, where p is varying from 0 to 2, delta y by 2 into 2 to the power 6 by 5, this is 2 to the power 6, minus 2 to the power 6 by 6. So this gives us epsilon sigma delta y by 2 to the power 6 into 2 to the power 6 into 1/5 minus 1/6. So these 2 to the power 6 terms, they cancel out. 1/5 minus 1/6, they give us 1 by 30. So this is giving us epsilon sigma delta y into 6 minus 5 by 30. So here we get the final version as epsilon sigma delta y divided by 30. Now, if I equals to 3, j equals to 2, then we get k 3 to e. This term becomes epsilon sigma into integration psi 3e psi 2e to the power 4 into d gamma re. This gives us epsilon sigma integration along minus 1 to 1. So psi 3e, this is half into 1 plus eta. Psi 2e is half into 1 minus eta. So this is to the power 4. D gamma re, this is dy. So dy equals to Jacobian delta y by 2. Determinant of the Jacobian is delta y by 2 into d eta equals to epsilon sigma delta y divided by 2 into 1 by 2 to the power 5 integration from minus 1 to 1, 1 plus eta into 1 minus eta to the power 4 d eta. So this gives us epsilon sigma delta y divided by 2 to the power 6 integration from minus 1 to 1, 1 plus eta into 1 minus eta to the power 4 d eta. Let us take 1 minus eta as p. This gives us d eta equals to minus dp. At the rate eta equals to minus 1, p equals to 2, and eta equals to 1, p equals to 0. So the limit changes as epsilon sigma delta y by 2 to the power 6 from 2 to 0. Now 1 minus eta was p, so this is p to the power 4, and d eta was minus dp. Now we are left with 1 plus eta. So here eta equals to 1 minus p. So this gives us 1 plus eta equals to 2 minus p. So here we can write it as 2 minus p. So this gives epsilon sigma delta y divided by 2 to the power 6 integration from 2 to 0. This is 2 p to the power 4 minus p to the power 5 dp. We can introduce the minus at the front. This gives us minus epsilon sigma delta y by 2 to the power 6. Here we have 2 into p to the power 5 by 5 after integration minus p to the power 6 by 6. So this is varying from 2 to 0. This gives us minus epsilon sigma delta y divided by 2 to the power 6 into, by putting p equals to 0, the first part becomes 0. So we are left with 2 into, this will be minus 2 to the power 5 by 5. Then the next portion will be plus 2 to the power 6 by 6. Then the minus sign at the front, it makes further change. This gives us epsilon sigma delta y by 2 to the power 6 into 2 to the power 6 into, this was 5, 1 by 5 minus 1 by 6. So this gives us epsilon sigma delta y divided by 30. So we got exactly the same term for K23E. It implies that the off-diagonal terms are symmetric, or the radiative boundary condition, it does not destroy the symmetry of the stiffness matrix at the element level and certainly at the assembled level. Now we are left with the term K33E. For I equals to 3 and j equals to 3, we have K33E equals to epsilon sigma integration along gamma RE. We have psi IE psi je to the power 4 d gamma RE for I equals to j equals to 3. This gives us K33E equals to epsilon sigma integration along gamma RE psi 3E into psi 3E to the power 4 into dy equals to epsilon sigma integration along gamma RE psi 3E to the power 5 dy equals to epsilon sigma integration from minus 1 to 1 half of 1 plus eta whole to the power 5 into delta y by 2 into d eta. This gives us epsilon sigma delta y by 2 integration minus 1 to 1 1 by 2 to the power 5 into 1 plus eta to the power 5 d eta equals to epsilon sigma delta y by 2 to the power 6 into integration from minus 1 to 1 1 plus eta to the power 5 d eta. Let us take 1 plus eta equals to p. So d eta equals to dp at the rate eta equals to minus 1, p equals to 0. When eta equals to 1, p equals to 2. This changes to epsilon sigma delta y by 2 to the power 6 integration from 0 to 2 p to the power 5 dp. So this gives us epsilon sigma delta y by 2 to the power 6 into p to the power 6 by 6, where p varies from 0 to 2. This is epsilon sigma delta y by 2 to the power 6 into 2 to the power 6 by 6 equals to epsilon sigma delta y by 6. So we have computed all four terms of the augmenting matrix. Therefore, the radiation matrix contribution to the element level stiffness matrix, we can write it as Ke radiation equals to K22E, K23E, K32E, K33E. This is T2E, T3E to the power 4. So this comes as epsilon sigma delta y by 6, epsilon sigma delta y by 30, epsilon sigma delta y by 30, epsilon sigma delta y by 6, here we have T2e, T3e whole to the power 4. Now we can combine this with the element level stiffness matrix due to conduction or diffusion. The augmented left hand side stiffness matrix may now be presented as KETE due to conduction plus KE TE to the power 4 due to radiation as K11E, K12E, K13E, K14E, K21E, K22E, K23E, K24E, K31E, K32E, K33E, K34E, K41E, K42E, K43E, K44E. Here we have T1E, T2E, T3E, T4E, plus we have the contribution from the radiation part. So the first part is from the conduction or diffusion. So this is a 4 by 4 matrix. We had a 2 by 2 matrix and 2 by 1 vector for the radiation contribution. Now, incorporating the T1 and T4 terms, we can represent the 2 by 2 radiation matrix as a 4 by 4 radiation matrix with 2 rows and columns incorporating 0 terms. So the first row corresponding to T1E, it will have all the zeros. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So the terms associated with nodes 1 and 4, they are all with zeros, and the remaining terms we fill here. So it is epsilon sigma delta y by 6, epsilon sigma delta y by 30, epsilon sigma delta y by 30. This is the 3-2 term, and the 3-3 term is epsilon sigma delta y by 6. And the vector from the radiation portion, it will be T1E, T2E, T3E, and T4E to the power 4. So this is radiation contribution. So this vector, it gives rise to non-linearity. Now we are left with the load vector. So FIE due to radiation equals to alpha QR double dot boundary integral along gamma E psi IE d gamma RE along gamma RE, where I equals to 2 and 3. So F2E for I equals to 2, it is alpha QR double dot integration. So this closed integral, it will be valid only from the path between nodes 2 and 3. So this is going from 0 to delta y if we think in the local coordinate system. So this goes in the natural coordinate system as minus 1 to 1. Then the shape function is half of 1 minus eta, and d gamma RE, this is dy. d gamma RE equals to dy equals to determinant of the Jacobian matrix into d eta equals to delta y by 2 into d eta. So this is delta y by 2 into d eta. This gives us alpha qr double dot delta y by 4 from minus 1 to 1 minus eta d eta equals to alpha qr delta y by 4 eta minus eta square by 2 varying from minus 1 to 1 equals to alpha qr double dot delta y by 4. Here we get 1 minus half minus 1 minus half. This is alpha qr double dot delta y by 4 1 minus half plus 1 plus half. So this is alpha qr double dot delta y by 2. Similarly, for I equals to 3, f 3e equals to alpha qr double dot integration from minus 1 to 1 half of 1 plus eta delta y by 2 d eta. This gives us f 3e equals to alpha qr double dot delta y by 4. This is eta plus eta square by 2 varying from minus 1 to 1 equals to alpha qr double dot delta y by 4 1 plus half minus minus 1 plus half. So this gives us alpha qr double dot delta y by 4 into here 1 plus 1 will be 2 and half and minus half cancel out 2. So this is alpha qr double dot delta y by 2. Therefore, the load vector for all 4 nodes of the boundary quadrilateral element may be presented as Fe due to radiation equals to 0 alpha qr double dot delta y by 2 alpha qr double dot delta y by 2 and 0. This is alpha qr double dot delta y by 2 0 1 1 0. So this is a 4 by 1 load vector. So we have illustrated the implementation of the radiative boundary condition for two-dimensional bilinear quadrilateral elements. Now the method which we have shown, this can be followed for performing the calculations using one-dimensional problems. Here we conclude today's class. We have illustrated the implementation of NBC and CBC in 1D as well as 2 dimensions. Both of these BCs augment the element level stiffness matrix but do not damage the symmetry. So symmetry of the matrix is preserved. The RBC introduces nonlinearity to the matrix equation system. Here, this is certainly radiative boundary condition. So this is RBC. For today's class, the textbooks by Professor Hughes and Reddy can be followed. Thank you very much for attending my lecture.